let's look at another frequency analysis with a second order system that we saw in the video. So with spring and mass, I typically like to show a vertical spring where we have some input y and some output x with a mass attached with mass m and a spring with constant k. If we had a spring set up like this, our transfer function y of s over x of s, or vice versa, because we have that y as our input. So let's go ahead and fix that. So we're going to have x of s, because x of s, the displacement of the mass, is our output. Y of s, the displacement of the top of the spring, is what we can control. We would have k over ms squared plus k. And so this is just also if we had a mass spring damper system, but our damping coefficient is equal to 0. Now, we can also visualize that same transfer function can be applied to the system or the three systems that we saw in the video, where the displacement y of s can be the displacement side to side that the motor induced on the mass, and the x of s is the motion side to side occurring, where it has that k over ms squared plus k pattern, and in this case the k is determined by the geometry of that of the thin supports. So we have this as our transfer function. We can standardize it a little bit and say that we'll have k over m s squared plus k over m. Now, in this example, we're going to have poles at s is equal to plus or minus square root of k over m. So it's a second order system where omega n is equal to the square root of k over m and zeta is equal to 0. And what we want to do is we want to visualize what goes on at different frequencies. So we're going to draw our real and imaginary plane. And our pole locations start off at plus or minus that k over n, and this should have a j factor because they're imaginary, because we would have that when s is equal to plus or minus k over m times j. That's going to be when we're at that point. So we now want to do, again, just like we did with that 1 over s plus 10 example, we want to see for different frequencies, how is our magnitude of our frequency affected, and how is our phase delay of our frequency expected. And if we start off at 0, again, this is similar to having a step function because we're not having a frequency input if our frequency is 0. Then our magnitude can be determined by, let's also just use some colors because we can. So we'll have 0 is going to be here, and we will draw vectors starting at our pole locations, and 0 locations if we had any. We don't for this example. Going to omega times j. In this case, that's just going to be that point at the axis. Now, the magnitude, g of s, or the magnitude of g, and we can say j omega because we know we're doing a frequency analysis, is going to be equal to a times the product of the 0 vectors over the product of the pole vectors. Which, for this example, the product of our pole vectors are just going to be those two L1 and L2. So we can call this L1 and L2. And we have no 0 vectors, but we do have an A, which is going to be determined by that k over m. So we can write, for all the situations, our A value will have a value of k over m for this example. So since our poles are at k over m, plus or minus the square root of k over m, if we multiply those together, we're going to have k over m for the product of our pole vectors. So for this example, it's going to be that it's equal to k over m over square root of k over m times the square root of k over m, which gives us a magnitude of 1. We have a pole that is going at negative 90 degrees for its angle, and for this one it's going to be positive 90 degrees. So because of that, if we draw with respect to horizontal, we have negative 90 degrees plus positive 90 degrees, so our phase angle is also going to be 0 degrees. Now let's say that we are operating at our natural frequency. So the natural frequency and the resonant frequency are the exact same if you do not have any damping coefficient. If zeta has a value, it can adjust a little bit, but in this class we're just going to treat our natural frequency as our resonant frequency because they're essentially close enough. We don't want to be operating at our natural frequency because it's going to have a huge amplitude anyway. So let's say that we are now going to have one vector, and so we could say j omega is going to be equal to our k over m, because that a is constant. We will have L2 has the length of 2 root k over m, and L1 is going to be 0. So the magnitude is going to be k of m over 0, which gives us a magnitude of infinity. So if we are operating at our natural frequency, then we end up having an extreme amplification of our output over our input, which is why we don't want to operate there. At this point, we can say that the angle starting at this pole going to the location is 0, and the angle here would be 180. So then we could say that our phase delay is going to be negative 90 degrees. And again, if we want to go to infinity, where we have a very fast frequency, so we're just going to say that that's somewhere at an infinite frequency, then our magnitude is going to be k over m over some infinitely long value, which would approach 0. And we would have two 90-degree angles for our starting at our pole locations going to our omega j value. So we would be at negative 180 degrees. So that's an example for a second order system. And in class, we're going to look at a Bode example of what this looks like with the tools in MATLAB.